Today we'll talk about cell potential and concentration, because we're going to find that as we manipulate the concentration of these galvanic cells, we can change our cell potential. The question is, how much can we change it, and how useful will it be if we're going to make a device such as a battery? So if we look at cell potential and concentration, we can say that under standard conditions, the cell with the reaction, and this reaction is going to be given by copper solid plus 2 cerium 4 plus in aqueous solution, is going to be in equilibrium with copper 2 plus in aqueous solution plus 2 cerium 3 plus also in aqueous solution. And I'm expressing this as an equilibrium, and in reality all of these electrochemical reactions are equilibrium reactions. Previously we really didn't have to worry about that too much, but now we have this particular equilibrium that we can establish, and we can discuss what's going on in this particular system of equations. So under standard conditions, this particular cell reaction has a standard cell potential equal to positive 1.36 volts. What we're going to ask ourselves now is what happens when we change the concentrations to not be equal to 1 molar, which would be going away from standard conditions. So when the concentration does not equal 1 molar, the cell potential will change. And we can investigate this in the laboratory. And what we would do if we were performing this in a lab would be we would set these concentrations equal to 1 molar. And then what happens if you dilute one of the compartments? That cell potential is going to change. And the question is, how is it going to change, and how can we look at this equilibrium expression to see which way we would predict a shift in that equilibrium? So if we increase the concentration of the Ce4+, this is going to drive the equilibrium over to the right, and as a consequence, we're going to see the cell potential is going to increase. So that's one change that we can, or one stress that we can apply onto this equilibrium. We can also increase the concentration of the copper 2 plus, or we could increase the concentration of the cerium 3 plus. In this case, we're going to drive the equilibrium to the left, and our cell potential is going to decrease. And this is a direct application and a prediction of Le Chatelier's principle. We can do the same thing with decreasing the concentrations and analyzing how this equilibrium will shift. So the question is, how can we perform a calculation on this and predict what the overall cell potential would be by changing these concentrations? What we do know is that from the thermodynamics chapter, we have a delta G is equal to delta G naught plus RT ln Q. And this is our Gibbs free energy reaction under any set of conditions. We also know that delta G is equal to minus NF E cell, and that delta G naught is equal to minus NF E naught cell. So we can take these values and plug them in to this equation. When we do that, we get minus NF E cell is going to equal minus NF E naught cell plus RT ln Q. So the chemists back in the day said to themselves, this is a kind of a brutal equation. What can we do to manipulate this and rearrange this so we can use a more convenient form when we perform these calculations? So what they decided to do is, okay, we have a particular equation. If we divide by minus NF in every single case, we get something a little bit simpler, and we have the E cell is equal to E naught cell minus RT ln Q divided by NF. And chemists still weren't very pleased with this whole mumbo-jumbo of variables. So in most cases, these reactions are performed at 25 degrees Celsius. So at 25 degrees Celsius, if we take RT divided by F and multiply this by 2.303, we get a value of 0.0592. So the equation that you typically see is that at 25 degrees Celsius, this is rearranged to say that the cell potential is going to equal the standard cell potential minus 0.0592 divided by N, where N is the number of electrons that are transferred, times the log of Q. This particular equation right here is very, very, very important, and it's called the Nernst equation. Now, why Nernst like logs and not natural logs, I'm not quite sure. But this is the equation that you will see represented in pretty much every textbook. And this will allow us to calculate the change in a potential when we vary the concentration. Okay? Keep in mind that that Q over there could be concentrations in solution. It can be partial pressures. So this particular equation opens us up to calculating a wide variety of problems. Yep?
Can you be a mix of partial pressures and polarity?
Yes, it can. Okay, depending on the case and what you have in your system, you can mix it all together. So if you notice in your mastering chemistry homework and your practice problems and your quiz, that Q is going to come in very helpful. Okay? We can calculate concentrations. We can also sometimes, from this equation, calculate the hydrogen ion concentration and calculate a pH. Okay? So manipulation of this equation right here is going to come in very, very, very useful.